So the next talk is Distributed Broadcast Encryption from Lattices by Champion and Wu, and Jeffrey will give the talk.
Hello. Hi, I'm Jeff, and today I'm going to be talking to you about distributed broadcast encryption from lattices, which is joint work with David Wu. To start, let's recall the notion of broadcast encryption. This is a form of public key encryption where we have many users, each with their own secret key, and the goal is to encrypt a ciphertext to a subset of these users, such that users in the set can decrypt, and users outside the set learn nothing about the message. Additionally, we want the size of the ciphertext to grow sublinearly with the size of the set. While this is a very natural extension of public key encryption, the traditional notion of broadcast encryption comes with a significant drawback. That is, there is a central authority who generates the secret keys for all of the users with some master key. This means that if the authority is compromised, security is lost for all users in the system. So it is natural to ask whether we can get a broadcast encryption scheme which has no long-term secrets. And this is exactly the notion of distributed broadcast encryption, or DBE, introduced by Bonnet and Zandri. In this setting, each user is going to generate a key pair as they would in public key encryption and post the key to some public key directory. Additionally, we allow the relaxation that these key pairs may depend on some one-time generated public parameters, but again, no long-term secrets need to be stored here. So the only real difference between DBE and regular broadcasts is just that encryption and decryption need to take in the set of the public keys associated with the set. Efficiency and security are entirely unchanged. So far, we've been able to achieve this primitive from strong tools like obfuscation and witness encryption, in addition to standard pairing-based assumptions. However, it is natural to ask whether we could get a post-quantum assumption potentially from lattices. So what we would really want to do is construct this primitive from learning with errors, or LWE, but after 20 years, we still don't really have an idea of even how to get centralized broadcasts. This motivated we and Sawbury to introduce evasive LWE, which was successfully used to construct centralized broadcast in the weaker public coin setting, and witness encryption in the stronger private coin setting. However, unfortunately, this private coin assumption was actually broken and partly patched already, so this is not a very trustworthy assumption at the moment. And sort of the happy middle ground right now is this L-succinct LWE assumption introduced recently by We to construct succinct attribute-based encryption. And in this work, we're going to construct distributed broadcast from this assumption. So what does this assumption say? It says that LWE is hard with respect to a matrix A, given a trapdoor for a matrix related to A, which we call D sub L. D sub L consists of L copies of A along the diagonal, concatenated with this tall and narrow matrix U, which is written blockwise in this picture. As a sanity check, this assumption is actually implied by LWE, if we take the U matrix to be very wide. However, in the parameters we need in applications, it is also implied by the weaker public coin evasive LWE. However, unlike evasive LWE, this is a falsifiable and instance-independent assumption. By instance-independent, we mean that it does not depend on a particular adversary like evasive LWE. Additionally, we can also get several applications from this assumption, including succinct functional commitments and succinct AB, as mentioned before. Functional commitments from the SIS variant of the assumption. All right, so now that we've gone over the assumption, let's get into the construction itself. So our starting point is going to be a centralized broadcast scheme, but we're going to sort of depart from previous approaches by taking a more direct and almost pairing-like approach. So the idea is as follows. Each user will be associated with a matrix W and a low norm vector R. The matrix W you can kind of think of as a user's like public key, and the vector R you can think of as part of their decryption component. Additionally, there's going to be some shared public parameters between the users, which just consist of random matrices and a vector, A, B, and P. So how do we encrypt? To encrypt a message to a set, we're going to use three components. A sort of helper decryption component, S times A, a component which masks the message, S times P, and additionally, a set-dependent component, S times B, plus the sum of WI for I and S, which we will refer to as the broadcast term. All right, so this is the construction so far. Now the question is, how do we decrypt? Well, we want each user in the set to be able to sort of uniquely compute this S times P term. And so the way that we're going to facilitate that is have each user that is in the set be able to generate a vector Y sub S that maps A to P plus BRI plus the sum of WJ times RI. Now, why would we want to do this? Well, now each user can compute S times P by simply subtracting the broadcast term times RI from S times A times YS. So the secret key for each user is just going to consist of a collection of vectors, YJI, where YII maps A to P plus BRI plus WIRI, and YJI, which is sort of like a cross term, maps A to WJ times RI. And to recover YS, if you're in the set, all you need to do is add up the relevant YJI components. As it turns out, because these sort of cross terms do not depend on P, it's actually all right to put them in the public parameters. And sort of simplifying the secret keys in this way will be useful for distributing the key generation procedure. And sort of as I just alluded to, this is still a centralized broadcast encryption scheme because these YIJs require knowledge of a trapdoor for the matrix A. So how are we going to distribute the key generation even though no one can know a trapdoor for A? Well, the approach is going to be to have each user sample their sort of public key component W along with the Ys which depend on W, namely their secret key, YII, and sort of the other cross terms, YIJ, that map A to WI times RJ. So the public parameters will now consist of A, B, P, and the RIs, and the public key for each user will be their W along with these vectors Y, which are the cross terms. Okay, so now we've basically reduced our question to just how do we sample W and these Y terms. And it'll suffice to consider a slightly simpler problem, which you'll sort of see why in a moment. And so the way we're going to do this is we're going to put a trapdoor for a matrix related to A in the public parameters. Why would this be useful? Well, consider our current relations that we have. If we imagine V to be a matrix which consists of L copies of A along the diagonal, then we can sort of set up the relations that we want as a linear system. And having a trapdoor for V lets us solve this linear system and get short solutions for it, which is sort of what we want. However, if we set V to be this matrix, we can actually target anything we want on the right-hand side, and so this is never going to be secure. So what we're going to want to do is restrict sort of what the YIs can target to vectors of the form WI times RJ plus H. All right, so how are we going to do this? Well, we're basically going to add additional columns to the right side of this matrix V. So suppose we add a column in this blockwise form, U1 through UL. This will additionally add a scalar part to the solution, which we will call D. And our relation, when we set the right-hand side to 0, if we set this UJ equal to the product of some random matrix Z and RJ, then by scalar commutativity, we can actually move D to the other side and set our WI to Z times D. The reason this is useful is because now we've sampled a whole matrix WI from just a scalar D, short scalar D. However, this is not going to be secure just yet because there's still a high chance of collisions since there's only so many W's that are possible. However, there's a rather straightforward solution, which is that we can just sample Z1, Z2, and Z3 and continue to add columns to the right side of V. And this will additionally induce solutions D1, D2, and D3 which we can then take the linear sum of to get WI. And it turns out, if we make this matrix V wide enough, we can actually derive its trapdoor from an L-succinct LWE trapdoor. Unfortunately, I won't have any time to talk about the security proof from L-succinct LWE other than this, but I encourage you to read the paper. So, to summarize, we get selectively secure distributed broadcast for L users, where the size of the public parameters grows with L squared, the public key size grows with L, and the ciphertext size grows independent of L. Some open problems include proving security from weaker assumptions like LWE, and more cryptanalysis and applications of this L-succinct LWE assumption. Sort of related to that last point, I want to advertise some upcoming work where we get registered ABE for circuits from L-succinct LWE in the random oracle model. And sort of the challenge here, in addition to extending the functionality of broadcast, is to deal with this issue of malicious keys. Additionally, these techniques generalize to adaptively secure DB. And with that, thanks for taking any questions.